Hi, Algebra 2. This is your second night of notes, and these are on imaginary numbers, but now we're going to go and do a little background on imaginary numbers and talk about what types of numbers they are, where do they fall in our number set, and then also what are some of the properties that apply to them. So go ahead and label your page. Your notes should be labeled as Day 2 or 3.2 imaginary numbers at the top. And we are specifically talking about number sets. And we're also talking about properties of numbers. Okay, and specifically we're going to talk about complex numbers. All right, so just make sure your paper's labeled correctly so we can continue. You guys have probably seen something like this in the past. The only difference is that when you guys were in middle school and then even in Algebra 1 in 9th grade, you really only dealt with real numbers. And real numbers are the numbers that you pretty much use on a daily basis for pretty much everything in life. We have something called rational numbers, and we have irrational numbers. And within the rational numbers are any number that can be turned into a fraction. I'm going to write fraction. Okay. They are also decimals that truncate, so they're decimals that stop. For example, something like 5.2. That stops. It doesn't go on forever and ever and ever. Or a number that repeats, like 0.77, but then I'm going to put the line above it because the line above it means it keeps repeating forever. So rational numbers are the numbers that either can be turned into a fraction or they're decimals that stop or repeat. Those are all rational numbers. The irrational numbers on this other side, these are numbers like pi or any kind of square root of a non-perfect square. So like the square root of 5, I can't simplify that. And if I put that into my calculator, I would get a decimal that would continue forever and ever, and it wouldn't make any sense. It would keep just changing forever and ever. So when you guys look at irrational numbers, they do not stop. They do not repeat. They're decimals that constantly are changing, and you can't predict the pattern. And then if you look inside the circles, any number that is rational, there are integers, whole numbers, and natural numbers that are also rationals. So integers, you know, are numbers that start in the negatives, but they're negative whole numbers. So you're not going to see fractions in integers. And then they're also positive, ... So 1, 2, and you can continue forever. But they're all whole numbers, negative or positive. And then to be an actual whole number, you have to be 0, and then you have to be positive as well. So we're getting more specific. You start with 0, and you can go up to infinity. But you do not include negative numbers when you're talking about whole numbers. And then natural numbers, the only difference between natural numbers and whole numbers is that we don't have 0. We start at 1. So sometimes natural numbers are also called counting numbers. When you guys were little and you first learned how to count blocks in your elementary school classes, if you were counting blocks, you wouldn't count 0 blocks. You would start by counting with 1. So when you call natural numbers, those are counting numbers because they're actually objects that you can count. Whole numbers add on the 0, integers add on the negatives, rational numbers add on fractions. Irrational numbers are in a different category of themselves. They're over here. But when you put rationals and irrationals together, you wind up getting real numbers. So real numbers include all rational and irrational numbers. And those are all the types of numbers so far that you've learned. Is this one rectangle, I'm outlining it here, this one rectangle includes all the numbers that you've learned up to this point in your life. In Algebra 2, we introduce the imaginary number, which is what you guys were working on last class. And imaginary numbers are the numbers that include i's. So I, any kind of square root of a negative number So for example, the square root of -9, we know that that would be 3i. So any kind of number that has an I in it, 5i, okay? Anything that has an I in it is an imaginary number. What happens though when we put together a real number and an imaginary number? I'm going to use green for this. If I take a real number and an imaginary, we put it together to make complex numbers. So complex numbers actually include every single number that we could possibly use in math. It includes the real numbers, and it includes the imaginary numbers. And especially when you put those two together, you wind up having a real part and an imaginary part. So I'm going to step back for a second and we're going to define this. If you guys look up at the top where it says complex numbers, let's give this a definition. So complex numbers are numbers that include a real and imaginary, oops, I'm thinking ahead, imaginary part, and they are in the form A plus BI. Okay, so I'm going to come down and I'm going to say A and B. So A is going to be a real number. A is a real number. Okay, and B is a real number as well, but it's being multiplied by I, so it is going to be the imaginary part. So we're going to say BI is the imaginary part. There we go. All right, pure imaginary is only the imaginary part of the complex number. So I'm going to say only the imaginary part of the complex number. And I'll draw a little line here just to make sure that we do not get confused, okay? So when I'm talking about pure imaginary, I'm talking about the I, the 5i, the square root of a -1. When I'm talking about complex, I'll put a couple examples in this box up here. When I talk about complex, I'm putting the two worlds together. So I could put 5 minus 2i. So 5 is my real part, and then 2i is my imaginary part. If I include, let's say, 1 plus 3i, that's also complex because 1 is the real part and 3i is the imaginary part. So it's putting those two together. If I wind up writing something like, let's say I write 4 plus 0i. Since it has 0i, so it doesn't have an imaginary part, it's still complex, but really that would just be 4. And if it's 4, then it would really be a real number. And more specifically, it would be rational. More specifically, it would be an integer. More specifically, it would be whole. And more specifically, it would actually be natural, because 4 plus 0i is really just 4. And 4 is a natural number or a counting number. So when we're talking about what types of numbers these are, you want to always pick the most specific category that you want to describe the number in. So there is our numbers, numbers in a nutshell, basically. We're looking at all the different types of numbers that we've used throughout our math career, and now we've added imaginary numbers to the mix, okay? So what are some properties that work with imaginary numbers or complex numbers in general? You guys have seen some of these properties for a while, so we are going to do a little review with them. The first property is, we're going to start with your first 3 that you are probably most familiar with. And the first one is the commutative property. Okay? And then associative and distributive. These three you probably remember the most. Commutative property talks about changing the order. So for example, if I have A plus B, that's the same as B plus A. And the way that I remember that one is because commutative starts with CO, and I like to think of that as meaning change order. So if we're getting stuck, commutative, also if you commute, you are moving, so we are changing order that we're in. So A plus B is equal to B plus A. It doesn't matter what order you add or multiply in. If I did A times B, it would be the same as B times A. So commutative property works for any complex number, any of the numbers we just talked about, if you're adding or multiplying. Associative property is when you associate certain numbers together. So for example, if I have A plus B, and then I add C, that would be the same as if I had A, and then I added B and C together. And what I want you guys to notice is that the order does not change. If I have A, B, C on the left side, I'm still going to have A, B, C on the right side. But what does change is the placement of my parentheses. This also works for addition and multiplication. So I'm going to say or A times B, and then times C, or A times B and C, okay? Associate numbers together could be a way that you guys remember it. How do I remember? Associate different numbers together. All right. And then distributive, probably the one that you will remember the most, but distributive property is always you're multiplying over addition or subtraction. So we have distributive property, we'll have A on the outside of my parentheses, and we have B plus C on the inside of the parentheses. And I'm going to actually distribute the A, so A is going to multiply the B, but because there's an addition sign between the B and the C, I'm going to add that to my A multiplying by the C. So I am thinking of that as multiplication over addition. If I had a minus sign, it would work the same way, but it would be AB minus AC. So multiplication over addition. Okay. Then comes our two inverse properties. We have the multiplicative inverse. And then we also have the additive inverse. Okay? Multiplicative inverse and additive inverse. I'm going to clump these two together because they are both inverses. And when we talk about inverses, I know a lot of you guys like to say the word opposite, but what we need to think of is if I'm going to multiply an inverse, I want to think about getting my identity as an answer. So what I'd like to do is come over to the side for a minute and take a look at an example like 4x equals 5. If I want to isolate my x, we always talk about multiplying by the inverse of 4. So when we multiply by 1 over 4, 1 divided by 4, that leaves us with our identity, our multiplicative identity, which is 1. So that allows us to have just an x on that side. And then, of course, we would multiply by 1/4 on the other side, and we would get our answer. Oop. There we go. Okay? So let's think about that in terms of my multiplicative inverse, since that's exactly what we have there. If I have A, and I want to multiply by some number to get 1 as my answer, I would need to multiply by 1 over A, 1 divided by A. So A multiplied by 1 divided by A is equal to 1, and therefore 1 over A is my multiplicative inverse. Think about that with addition. What would I add in order to get my identity for addition is 0. So what can I add to A to get 0? My inverse would be negative A.